if there are no any questions, so today we're going to focus on this experiment. Okay, experiment conducted for the difference between the EMF, the electromotive force, and the potential difference. Okay, so the last lesson before we finish the lesson, I already told you try to compare the result with the Ohm's law. Because the Ohm's law, you will get the graph V against I, which is the linearly proportional under the Ohm's law. But when it comes to the EMF experiment, our graph V against I, it becomes decreases linearly. So we want to know why it becomes like this. Okay? Why the graph V against I, it becomes different result. Right. So now look at here. Okay, so before I straight away focus on the EMF, okay, we go back first. We go back to Ohm's law to recall back your memory. Okay, you look at the Ohm's law experiment. This we have the ammeter, and we connect us close the one resistor wire, which is this resistor wire have the constant R. And after that, we also have the one rheostat is used to control the current flow in the circuit. So after that, this constant resistor, right, resistor wire, we connected closely with the one voltmeter. So with the rheostat that we have, when we increase the current, right, so the voltage across this constant R resistor, then we will get the relationship close circuit currents and the voltage reading that we have, V against I, we get directly proportional result. With the gradients of the graph is a constant R. Okay, so this is what you learn in the electron. So now I want to pull your focus to the other side. Which is I want you to focus on what happened on the voltage across the fuse. What happened to this voltage? Maybe I can put it as a V. So this one I put it as a V1. So what happened to this V2? The voltage across. What happened to this V2? When our current increases. Let's guess. What happened to this V2 when the moment current increases? And respond. Again, I repeat again. Look at this circuit. Maybe you need to copy down, right? Because once I change the screen into the room, so you won't see this circuit anymore. So I give you a few seconds. Try to copy down faster. Question is, what happened to the V2 when the I increases? So before I go to the chat room to see the answer, I know that some of you is already typing the answer. So, okay, I want to discuss here first before I go to the chat room. Okay, you see, for the overall circuit here, why the rheostat able to control the current flow? Okay, why the rheostat able to control current flow? Okay, the idea is the rheostat itself actually is an adjustable resistor. So that's why when we adjust the rheostat, actually we are changing the circuit effective out. We are changing the circuit effective out. So if I put the rheostat resistance as the R2, it means I have to change this one as the R1. Okay, R1. Okay, R1 is fixed. R1 is fixed, right? if we assume there's no change on the other physical condition, example, especially the temperature. So that's why we assume that the R1 across this resistor wire is constant value. Right? Constant value. Okay. But the rheostat is the adjustable resistor. Right? So that's why when we adjust the rheostat, we are controlling the current flow. Right? We're controlling current flow. So the circuit has the effective V. And this effective V is equal to this constant, this current, only one current here, V equal to IR, right? So multiply the effective R of the circuit. R1 plus R2. Right, R1 plus R2. Effective R of the circuit because connected in series. So now you see here, when the moment, remember, R1 is a constant, so I constant it. R1 is a constant, it cannot be changed. R1 is a constant. So when the moment I adjust the rheostat, okay, the effective V of the circuit also constant, it won't change. Right? So we focus here. Effective V also constant, it won't change. Right? So when the moment I adjust the rheostat R2, I'm able to change the current. How I get to increase the current? I must make the R2 bigger or smaller so that I can increase the current. Answer this one first. Right? What I have to do on the output so that I can increase the current in my this experiment. So that when I just adjust the start, so I have to increase the current slowly 1, 2, 3, 4 for the 5 difference I, so that I can have the 5 different V1. Then I can follow the graph to complete my own law experiment. Okay, so in this case, how I'm going to increase the current by the calculation that I know here. What happened to the output so that the I will become higher? What happened to the output? So yes, output have to make it smaller. Okay, output have to make it smaller, then the current, effective current of the circuit will become higher. Right, so you got the idea already. So it means I have to reduce the output. Then only the I will be increased. Right. So when the I increase, you see, anyway, this one only for notes. You cannot use like this in the answer for exam. Because the arrow, it doesn't presenting the meaning of increase or reduce. Arrow actually pointing the directions only. Right. So as a note, okay, as a for the understanding, during the our learning like this, so I will use a arrow, assuming there is an increase and reduce. So, but during the exam, we cannot do so. Right? Okay, so anyway, the V1 is based on the result of I multiply the constant R1. So that's why when the moment R2 smaller, we increase the current. So that's why you will lead us the V1 become higher. That is the Ohm's law result. Higher the I, higher the V when the resistance is constant. According to the this experiment that we conducted, we need the auto so that we can vary the current. So we use the auto to vary the current to increase the current. Then the currents will be respond on the potential difference across the resistor wire. So it makes the V1 across it also increase. This is what we learned in the Ohm's law. So now my question is, what happened? At the same time, what happened to the V2? V2 is equal to what? V2 is equal to the same current multiply the R2. So now the problem is R2 is decreases because we adjust the rheostat to increase the current for our Ohm's law experiment. We lower down the rheostat resistance, so the effective current of the circuit will be increased. Then we measure the voltage across the constant resistor wire. Then we have the result V directly proportional to I. There's Ohm's law. But we doesn't connected a wattmeter, another wattmeter across the rheostat output. Now I want to ask you, what happened to the output? Actually, so now you can see the result here. We adjust the output lower down the output, then effective I increase. And then the V2 is determined by the effective I multiplied the output. So what happened? What happened to the V2 now? What happened to V2? What happened to the V2? V2, for the moment, as I show you here, V2 is the product of the current across it multiply the output itself. Now the problem is output is changing, current also changing. Output lower, current higher. Output lower, current higher. Output higher, current lower. So when the product is showing the V2, so what happened to the V2 for this product actually? It seems like it becomes constant, is it? Because one higher, one lower, one lower, one higher. So they are multiplied. It seems like macam constant. So when I mention like that, you know the answer constant is wrong, right? Okay. Because it macam constant, but actually it's not constant. Because of what? The only constant in the circuit is effective V and resistance of the resistor wire that we connected. Unless all is a variable, it will depending on the colors, depending on the output, right? So unless all actually keep changing, there's no such thing that others quantity will be constant in this circuit, others than hour and effective V. So anyway, you see here, okay. So the V is effective V. This effective V, because it's a series connections, right? It's a series connection is equal to the V1 plus 2. And we are very sure V1, when the moment current increase, V1 is increasing. So we want to know when the current increasing, what happened to the V2? So when you look at the result, then you should know already V2 is increased. Then only their sum is still equal to constant V. Now we're talking about the sum at when total V1 plus V2. When the moment V1 increase, V2 definitely have to decrease. Then only V effective V of the circuit is still remaining constant. So one of the learning objective here you have to keep in your mind. Where you have the one formula or the one equations, for example for this V equal to IR, when these two quantity, these two physical quantity, both are changing, then you cannot guess their product result. Because you don't know the changing is bilateral or it's not linear. Right? So you cannot say that, okay, when the R become from 2 become 4, so the I will be from 1 become 0. Increase, decrease one. So you cannot make the assumption calculation like this. What I can tell you is when you have the equation something like this, and in the equation there are the two variables or the two physical quantity is changing, and then these two changing quantity you have to multiply or divide each other. Then you cannot guess the result. You must know exactly what happened. You cannot by just guess. But for the V like this, V equal to V1 plus V2, right? V equal to V1 plus V2, yes, because they are no multiplier, they are not the product. So they just only V1 plus V2. So equal to the one constant sum. So then when the one of the quantity increase, the other one quantity definitely have to decrease. Then only their total sum still equal to one constant value. This one for the mathematical for sure we know. Right? But the product multiply or divide you cannot guess in that way. Right, remember? Okay. So now we want to know why the V1 increase, V2 is decreased. Because the V2 actually is equal to the effective V minus V1. Effective V minus V1. So that's why when the moment V1 increase, but the effective V constant, so constant minus getting bigger value, so you will get the result V2 will decrease. Right? V2 actually decreases. Right? So V2 actually decreases. And this one is really important for you to understand why we have the result for the EMF experiment. V decreases linearly with current. Okay, so now I'm going to lead this one into the understanding about the EMF experiment. Okay, so there you see what happened. So I draw again the circuit. Please remember this one. Right, V2 actually equal to the effective V minus V1. Okay, so now look at the circuit here. Just now we our Ohm's law experiment circuit is like this. We have the V across it, right? So I put this one. So V1. Right. Okay, so and after that we have the V across this one. And V2 closer to your start. Okay, so this circuit, if I try to make it a little bit changing, which is I shift the position. I pull this R, I put this R, make it closer connected with the. It's still connected in the one CD circuit, but I change the positions on it. So I put it side by side. Okay, I put it side by side, and then I change it becomes a symbol for the resistor. Okay, and I have the resistor. Okay, here's the resistor. So here is our V2. And this one is our V1. Here is still our V. Is it okay for you if I show like this? Actually, the understanding is still the same. Okay, now. Now, if you notice that this one actually is an EMF experiment. Because of what? The resistor I show here actually is the internal resistance. Internal resistance. Right? So for the battery. Internal resistance of the battery. So like this. The slider, the way we conduct the EMF experiment. Okay. This battery, okay, different with the battery inside here. Okay, it's different. Right? It's different. Because of what? This one is physically assist. Physically assist. Physically assist. Okay. So when we connect the V2 like this, actually we connected to across this point. This point is the same that we connected the voltage across, voltmeter across here. It's the same. It's the same connection. It's the same connection. Okay. And then here I just try to show you. I just try on the left hand side here. I just try to show you what happened inside the battery itself. I'll show you what happened to inside the battery itself. Inside the battery itself, we have the one. This green color V is the one actually we call it EMF. And then inside the battery itself have the internal resistance. So when the moment, okay, listen up. Now it's very important for you to understand why you get the result. V higher, I lower. Right? Okay, this is nearly the relationship. Okay, so as a continue for our previous lesson, when the circuit is on, the currents flow through the circuit, it need to overcome the internal resistance. So part of the energy will be lost as a heat due to the internal resistance. And this one we call it work done against internal resistance. Right? Work done to overcome the internal resistance. So since we have the resistance, means there will be the work done for the charge. Work done for one coulomb of charge across 2 points. Means across 2 points here is across the internal resistance. When the moment we switch off, current, there's no charge flow, so that's why we have no current. Then internal resistance is not bring any effect because of V1, the V1, the blue color V1 will equal to 0 because there's no current. Then what we measure across the voltmeter, it will show you the result of the EMF. But the moment we switch on the circuit, the charge flow in the circuit, so now we have the current. And the current across the internal resistance, there will be the V1. It's the potential difference, or we call it work done over the charge across the internal arc. So it's a V1. At the same time, also have the charge flow through the rheostat. So we have the V2. Then the V2, the result showing actually is the constant EMF minus the V1. And the V1 because V1 is across the constant internal arc. Okay, V1 is a constant internal arc. So that's why when the higher the current of the circuit across a constant arc, the potential difference across it will be higher as well, according to the Ohm's law. Right? So due to that, when the higher current, higher V1. So higher V1, E minus V1 equal to V2. So that's why the V2 will be lower when we conducted this result. Right? Okay, now. Here, the V2 result, or the I put the orange color V lah, right? Color V, V2, V actually is equal to what? actually equal to the result of the E minus V1. Right? And the V1 actually is what? V1 actually is equal to the current multiply constant R. So when we adjust the rheostat, R just now, when adjust the rheostat R, when we lower down the rheostat R, we increase the current. Right? We increase the current. So that's why when we increase the current across the constant R here, is a V1. V1 also increase. Okay? V1 also increase. Okay, V1 also increase. Because Ohm's law, remember, Ohm's law only apply on the constant R conductor. When the current flow through the constant R conductor, the relationship between the V and I will be directly proportional. This is Ohm's law, only apply in the constant R. So our internal resistance is a constant R, so that's why when we adjust the rheostat, current increase, voltage across the internal resistance will be increased as well. So, and straight away will affect on the result of the V2 because our V1 increase due to the increase of I. Then it will cause our V2 come lower. Because EMF is a constant. So that is your result. When we study the V, orange V, across the I, when the I higher, V is lower. So that's why we have the result like this. Okay. So when we study across a constant R, which is our blue color V, color, so we have the directly proportional result because it's a constant R. Right? Okay. And for this graph, when the V decrease nearly with I, you'll notice that when the I equal to 0 is here, right? When the I equals 0 here, I equals 0 here, the intercept of the V axis here or the Y axis here is our EMF. Because of what? When the current equal to 0, our V1 will equal to 0. When the V1 equal to 0, V orange equal to EMF. V orange equal to EMF. So there is a graph according to the EMF experiment result that we have. Y is decreases linearly. So this graph that we have, if we compare to the general equation of graph that you learn in mathematics, Y against X, when we have the line result like this, the graph result like this, so this one intercept we put as a symbol C, right? So what is the general equations for this graph? We will have the Y equal to negative mx plus c. Is it? Yeah. Okay. Orange V is equal to the V2. Yes, yes, yes. Orange V is the V2 in the diagram that I show you. Yes. Right. Okay. So now we compare these two graphs. V against I compared to the Y against X. Y against X, we have a result like this. This is our equation. Then if we try to change whatever that we have here into the equation, what you get? You will get V equal to negative M I plus E. Right? So if you rearrange a little bit, then you have V equal to E minus F I. So this one actually is means this N, this N actually is our internal resistance. So means the gradients of the graph, here, and this gradients of the graph actually is equal to resistance, internal resistance of the circuit. Right? So it's a positive value because the gradient is a negative. So how to say? Based on this one, okay, you see, based on this one, we got the negative M equal to negative R. But we have negative because we know that the graph is a negative gradient. The graph is a negative gradient, right? So that's why the formula becomes negative M. So when we calculate the result, we will get the M is negative, right? Here the M will be negative. So when you substitute the negative value of the M, so you will get the positive resistance, internal resistance. Right? So remember, when we come to the calculation part, when they doing the gradient, some of the students they will show the internal resistance one negative value, but negative value of the internal resistance is wrong because in the equation we already know that it's a negative gradient. So that's why when we do the calculation, actually the gradient magnitude itself is presenting internal resistance, is not the negative sign. Alright, okay. So in the partial SPM, they always give the question like this. Partial SPM give you the graph V against I like this. Then afterward, it asks you to determine the gradient. One of the paper 3 questions, paper 2 question. You ask the student to determine the gradient. So the student will be calculate. So you will get the answer. Let's say M equal to negative 2. Negative 2 V voltage over ampere. V over ampere. Right? Because current is ampere. Then after that, the next question, it will ask you to determine internal resistance. It will tell you the internal resistance equal to negative M. Right? So determine the internal resistance with the gradient that you get. So when you do calculation, negative M is what? M is negative 2. That's why you will have the R equal to the 2 ohm. There's an internal resistance of the circuit. So this question, it came out few times in RCSPM. Right? Paper 3. Paper 3. Okay. And then also one of the very, very popular mid-year paper 3 questions or trial paper 3 question as well, especially the mid-year. So for my experience, most of the school teacher, they will use this graph as a paper 3 second question. Mid-year paper 3 second question. So means for our school, since I told you already, it will be not possible at all for me to come out this question. It's just a hint for other school. If you want to helping your friends, okay, so just tell a friend. Later on, mid-year exam, if the teacher is already covered the chapter 2 combined electricity, then the mid-year exam paper 3, most possible they will come out the question 2 for this graph. Right? Okay. So nothing to worry about. Paper 3 is just only calculation. You not study the book, no at all, also can be answered because based on your answer. So okay. So I hope that I'm able to post this video to upload to YouTube soon so that you can revise back what I told you, right? What I conducted for you. And okay, so that is the equations involve the calculation. But remember this equation is not given. It's not given in SPM formula list because it's a part of the understanding in series circuit. It's a part of the understanding in series circuit. Why I say so? As from the beginning, I told you, I show you. So now I try to go through again. They understand why the formula is minus. Okay. In the normal circuit, we have the R1 output. So V, V1, V2. So normal series circuit, we know that the V is equal to V1 plus V2, which is V2 or the V1 like this, V1 equal to the V minus V2. Right. In the normal series connection circuit, this one is very easy for you to understand. Okay. So now if I try to change a little bit, I put the output next to the V that I have. And I still have the R1 here. Okay. So when I connect the voltmeter across R1, so I should measure the V1, right? Okay. And then this connection is the same as a connection. I cover these two. The same connection. But the problem is, when I cover these two like this, I write here V and V2. The V across output, right? How you detect the V and V2 with the V1? Okay, how you detect the V, V2 and okay, V1. So if you don't know, if you don't understand from the beginning, right? If you don't understand from the beginning, then you will thought that oh, V1 is cover the V and V2. So the V1 is should be equal to the V plus V2. You may talk like that because it's cover one. But you're wrong. Because in this circuit, the only one effective, this one is wrong. This one is wrong. Because in this circuit, the only effective or only the highest value V is this V. So it cannot be V plus V2 equal to V1. So due to that, I try to let you understand from the beginning like this. V equal to V1 plus V2. And then to know the V1, it must be the V minus V2. That's why when I put the output next to the V to let you see, so you should able to understand that V1, it should be equal to the V plus V, sorry, V plus V2 plus, okay. V minus V2, right? It's not the V plus V2, this one's wrong. This one's wrong. Okay. So, and if you try to see the output as an internal resistance, because internal resistance is inside the battery, we cannot measure physically. We only measure their result when I connected, when you switch on the circuit. Internal resistance, how much is the V? We cannot measure physically. We only get their result after the circuit overcome the internal resistance. Right? Okay, so we only measure is after they overcome the internal resistance. So that's why we try to understand this as what happened in the battery. So it becomes like this. So if you try to understand this as an internal resistance, we try to presenting in our circuit, because physically you cannot show, you cannot measure across it. Right? So that's why usually we always want use a dropper line to box it. Okay? Because physically we cannot measure across the internal resistance. This one. Right? So when we connected here, this V1, right? So this V1, it's just like the way we connected a voltmeter across the battery. Where here I try to change it into the rheostat so that I can vary the current to know what happened to the voltmeter result. So when we vary the rheostat to change the current, increase the current, the result V that I have for getting less and less when the current getting higher and higher. Because of what? When the current getting higher and higher, the I multiply R result will be higher. I multiply R result will be higher. So that's why when I adjust the rheostat, increase the I will get the lower V, because the V is equal to what? The V equal to the EMF here. This one, the EMF minus the IR. Okay, minus I. So that's why when the I higher, it will result the V getting lower. E is a constant. So why this equation it doesn't provided in the exam? It doesn't provide in the exam. So now I let you know the reason why it doesn't provide it. If you don't understand, you already know why it doesn't provide it. Because it's a part of the series circuit that you study. Okay. So now we practice. We practice the calculation. We practice the calculation. Okay. So we start from the normal circuit first. We practice the calculation. Okay, let's say I have the 5 ohm here, and I have the okay, 10 ohm. Yeah. Okay, 5 ohm, 10 ohm. Right? And the current in the circuit. Okay, current in the circuit, 2 ampere. Okay, how much is the voltage there? How much is the effective potential difference of the circuit? How much effective potential difference of the circuit? Right. So don't give up. I know that it's not that easy for you to early morning wake up straight away, look at the so many formula like that. Okay. So some of you may be upset or you will give up already. So don't worry. Now we try again with the calculation. I think with the number will be much better for you. Right. So now you just tell me what is the effective voltage. Why I keep saying effective voltage? Because this one is the result after the EMF minus put down against internal resistance. That's why we say so effective voltage. Okay, according to this circuit, we how much the effective voltage? Right. So effective voltage it should be 30 watt. 30 watt. Right. So Lulu Achika don't answer me 30 only. Okay. If you think also don't answer 30 only. Remember always with the unit. Always with the unit. Okay. Virginia also same. Okay. Always with the unit. Remember. Okay. I know at exam you should alert. Okay, for the responding now, maybe 30 is fine for you. Alright. But I hope that you always remember must come with the unit. Okay, so that's why here we know that the V is equal to the 2 multiplied plus 10. Right? So that's why equal to the 30 watt. Okay. So now, okay, like this. 5 ohm is still the same, 5 ohm, 10 ohm is still the same, and then the current is still the same, 2 ampere. Right. So only the difference is here. This one, I change it, I show you the what happened inside the battery. I show you what happened inside the battery. Right? I show you what happened inside the battery, which is inside battery. Right? Actually, there is a internal resistance. So now, if I tell you the internal resistance is a 2 ohm. Internal resistance equal to 2 ohm. May I know how much is the EMF of the circuit? This power supply. EMF of this power supply. How much is the EMF of this power supply? What the answer is? Okay. What can you join our meeting? Too many people. How many people here? 97 only. Right. So you get the EMF equal to 34, right? Okay, 34. Is it correct answer? 34 watt. Right. So now this one, the EMF of the circuit is equal to current multiply 5 plus 10 plus 2, including the internal resistance. Right. So that's why the EMF actually is 34. 34 watt. Means actually how much is the work done one coulomb of charge across the internal resistance, or we call it potential for the internal resistance. Actually equal to the I multiplied internal resistance, right? So it's a 2 multiplied 2, 4 watt. So that's why you see the result effective V, which is effective 30 watt. Effective V actually is the result of EMF minus voltage across the internal arc. So that's why it's equal to 34 minus 4, which is equal to 30 watt. 30 watt. As you calculate the effective V just now. Right? And for this question, you also can try to think, if I try to connect a voltmeter across a battery, when the moment I switch on, a voltmeter across a battery, when the moment I switch on, what is the reading of this voltmeter? When the moment I switch on, what is the reading of this voltmeter? So when the moment I switch on, the circuit is on, what is the reading of the voltmeter here? Right? So only Amanda answer 30 watt. Right? Okay, yes, it's 30 watt. 30 watt. When the moment I switch on the circuit So the voltage across the voltmeter, so it will show that it's a 30 watt. Then what happened to the voltmeter reading if I switch off the circuit? When the what happened to the voltmeter reading when I switch off the circuit? It will become 34. It will back to the 34 because when the moment circuit is switched off, there will be the no work done against the resistance. So whatever that we measure, it will be the EMF. That is why in our previous lesson, we have the one conclusion: the EMF practically always higher than potential difference. Because potential difference is the effective V after the EMF, after the charge uh, overcome the internal resistance. Right? So by ideal conditions, EMF always equal to PD or equal to potential difference. Because by ideal condition, we assume there is no internal resistance. When there is no internal resistance, when you switch on or switch off, there will be no work done to overcome internal resistance. But practically, so somehow we cannot avoid internal resistance. So that's why when you connect a circuit, when the charge flow in the circuit, it will be the work done to overcome the internal resistance. So that's why the effective V that we get, it will be less than the ideal condition. So due to that, practically our potential difference always less than EMF. So I hope that you have the better understanding now. Okay. So seems like this morning quite a lot number of you internet connection not strong. Okay. So if you're using your handphone, try to come out from your room. I know that just wake up early, maybe you just on your handphone in your room, right? So that's why the connection signal is not strong. Okay. So when you switch off the circuit, yes, okay, Radisha, I know that just now you left already, now you come back again, right? So when the moment we switch off the circuit, okay, the voltmeter reading will be 34 watt because what we measure now, the moment the circuit is switched off, what you measure is EMF, electromotive force. But when the moment when you switch on the circuit, okay, there will be charge flow in the circuit, so it will be have a work done to overcome internal resistance. So what you measure will be the effective V only. It's what we call potential difference. Work done across 2 points. Okay. But the problem is you cannot measure work done across internal resistance. What you measure is a work done across a battery. Right? But when you switch on the charge flow, so that will be the inside the internal battery itself have the internal resistance. So will we have the internal work done. So we have to minus it. By theory, we know how to minus it. Practically, we only see the result, higher, lower, on, off the moment. Okay. So we try to understand what happened here. Why the same voltmeter measure across the battery with the moment on and off, the reading will be different. Yes. This is because of the internal resistance. It causes you the result show on the voltmeter. Either it's potential different, either it's a electromotive force. Right? So that's why, okay, I show you so many the way how to understand it. I hope that you take some time, try to digest all this. Okay, hopefully you have the better understanding. Okay, if at the end still cannot, then what to do? You just have to know how to do the calculation and must just memorize the result for the EMF is a decreasing linearly V versus I, and the Ohm's law is directly proportional for the V versus I graph. That's the only way I can try to help you to score exam. But anyway, I hope that you are not just focused on scoring exam, but you able to understand what happened and what's the difference between the potential difference and EMF. Okay, so you see, when the potential difference, our formula W over Q. For the EMF, our formula also W over Q. But based on the definition, on the potential difference, the W over Q will say so work done per one coulomb of charge across the 2 points in the circuit. Again, for the definition of potential difference, according to the formula that you have here, our explanation for this potential difference will be work done per one coulomb of charge across 2 points in the circuit. And the EMF is energy provided for every one coulomb of charge by the source. Again, for EMF, is the one we call it energy provided by the power source or by the source for every one coulomb of charge, or per one coulomb of charge also can, to round the circuit. Right? So that's why in ideal conditions, a battery, when we're talking about across these 2 points, right? In ideal condition means we assume there's no internal resistance. In ideal condition, these 2 points, what you measure is the EMF, right? So it's supposed to measure what is the energy provided by the battery source battery here for every one coulomb of charge, for every one coulomb of charge, in ideal condition, right? Okay. At the same time, if I want to measure these 2 points across by the conductor here, so I able to know what is the work done by one coulomb of charge across 2 points. How much the work done by one coulomb of charge across these 2 points in the circuit, right? So when you look at the connections, they are connected across the same 2 point here, on the orange color side and also on the green color side. That's why in ideal condition, V and the E they are set. But the problem is, practically, we not really measure EMF. Because practically, what happens in the battery is inside have what? Inside the battery have internal resistance. That's why what you measure is only the potential difference. What you measure across the battery is only the potential difference. Right? So you measure across a 2 point potential difference. Okay? Because of the internal resistance. So there will be work done to overcome the internal resistance. So what you measure, you have to minus. So that's why the voltage or equal potential is different, always is less than EMF. Because EMF is exactly inside here. Only the moment you switch off circuit, there's no current flow through the internal resistance, so there will be no work done across the internal resistance. Then you measure will be the EMF straight away. Because the V across the internal arc becomes 0. So we don't need to minus the V across internal arc. So you measure E minus 0. So that's why the result will show you E. But the moment you switch on circuit, what you measure on the voltmeter is a E minus V for the internal arc. Right? E minus V of the internal arc. So that's why what you get is the result E minus V across the internal arc. But done across internal resistance. So it will be less than the actual EMF. Right? So E only equal to V in ideal condition when we assume there's no internal resistance. Right? Is this okay for you? Right? So I think definitely you need some time to digest it up. Right? So unless you already put some effort, try to understand before I teach you. Yes, yes. Put on the mic. Do you have any question to ask? Somebody on the mic already. After switch off again. Okay. So let's see. What else you have to learn here? Okay, so all this you can just go and study lah. So if you need the answer to fill up the blank, so maybe you can do so now. Okay, so you just print screen and then you paste. Okay, next time for those use a laptop, right? If you don't want to watch back the videos or what, or you're lazy to drawing the ligand, okay, or you want to do it later or what, you can use your keyboard, print screen, and then open the Microsoft Word, and then you press the print screen one by one. So after that, after finishing the class, you can take your own sweet time, go through again by again, and then to complete your own note, right? So that is a way how you manage up. Okay, so if you really don't want to wasting time to go through the video again, right? So I hope that you already understand what happened to the circuit diagram the given in the module, right? Okay, so basically for the EMF, we just finish here. Okay, so take all the question. Okay, unless the question mentioned under ideal condition, we have to do it with the okay, as is the real condition. Alright, okay. So actually, when it comes to the exam, so you don't need to worry about whether the question give you under the ideal conditions or not. Okay, it's very simple. Okay, just now I let you see that the mixed connection. Okay, right. Okay, someone remind me about the attendance already. You're so worried about the attendance. Alright, okay. So I gave you the link now. Okay, anyway, thanks for the reminder. So because of 9:35 already, so we have left for 10 more minutes. Uh, I give you now. Okay, thank you for the reminder. Okay. At the same time, you listen to me also when you fill out the attendance. Okay. How? Okay. So when the SPM question asks, if there's not any information regarding the EMF or internal resistance, so you just solve it as a normal parallel series circuit. Just go ahead, no problem. Because anyway, there's not any information for you to do, nothing to do with the EMF and internal resistance. But when the moment the question show you there is tell you there's the information about EMF and internal resistance, then you have to do the calculation by involving the internal uh, resistance in the EMF. Right? Okay. So I give you 1 minute. Try to fill out the form now. So later on I will show you another question. Okay. So this setting is only for those joined with MOE ID. So if you are not joining with MOE ID, you cannot fill out this form. So maybe you need to copy now the link. Then only that you can fill out the form later to make sure that you are signed up with the MOE ID. The resume, I don't think so. You are joining the meeting with the MOE ID. Because if you're joining with MOE ID, so the name behind your name will be the name same exactly same as the IC, and the ending with the MOE. Right. So if you are not joining with the MOE ID, you cannot fill up this form. So let's see. What? Oh, already past 78 already. So any more? Some more coming. Today attendance not so good, Only 78 of you, When I look at the people here got 90 plus, I think some maybe it's the other school students. So if you're other school student, you're using the MOE ID joining, so you also can fill up the form. Just for my own record lah. Included if there's any teachers inside here, also can fill up the same form. Right? You also can fill out the same form. Just for my records only. So I should receive around 95, 80. So still some more is coming in. So there's one teacher's sign already. Okay, one school, still only one school. Is there any other school students? So we have two other school students. Thank you for joining us. I hope that you can learn something. The student from the USJ Ed. Okay, this student from the USJ Ed, please tell your friends switch the classroom, because the previous classroom I noticed there are some outsider joining that we don't know who are them. So that's why now I want to force everyone using the MOE ID. So that's why we already switched our class to the new classroom. So today you get the link to join this meeting because the announcement I made in the new classroom you already joined. But I noticed that many of your classmates haven't switched the classroom yet. So try to inform them. For those still want to join in my class, you can change to the new classroom. I already made an announcement in the previous classroom. So there's a class code there. So ask them join with the MOE ID. Okay, thank you. Huh? You allowed to submit the form, man. I check my setting. No, my setting is only allowed to MOE. So I think because of your handphone or your laptop actually have the uh, two IDs added. Okay, so that's why you still can sign up the form. But actually, I already restrict. You only can sign up by the MOE ID. Right. So, okay, so I come back again. Okay. For 84, still some of you haven't signed up yet. So maybe of the ID problem. So you keep trying now, huh? Right. So make sure you sign up the form. Okay. And then please don't need to wasting your time, copy down and keep this form for the next lesson. Because the next I will change the link again. I will change another form. You force me to do so because some of you really cheating. And also send that now in the meeting room got 98 people, but the attendance only 85. Assume that some is already left the computer or the handphone on, but don't know where they are already. So it's already missing in front of the screen. Uh, so anyway, let us continue the last reminder for you. Okay, when the questions there's no mention anything about EMF or the listen, you don't need to worry about that. You just carry on the solve the problem as usual. Okay, only when the moment there is an internal decision and the EMF information given, so you have to use it. Alright, so the next lesson I will touch a little bit uh, for the problem solving, okay, by calculation. I will give you some cases to do some practice. Okay. And before we go to the next subtopics, electrical energy and the power. Yeah, basically, electrical energy and the power is totally just a formula. Totally just a formula. Right? So do the problem solving. Right? So you can see there's a list of formula I give you so much formula. During the exam only give you one. Right? But the others we only substitute the previous equation into the only one equation, so it will become the so many others formula. Right? So but during the exam it's only give you a basic. This one just only substitution and then transform the formula. And in the same chapter also we're going to calculate the power rating and then also the energy consumptions. So especially now it's very important for you to know about how to calculate the electric field. Right. Recently, our PM already announced that there will be the discount. There will be discount for the coming April electric bill. Right. So many people don't know how the discount is working, and then they are put some so many different assumptions. Right. So for the next coming lesson, please prepare one of your house electric bill so that we can try to study how to understand the electric bill and how is the discount is working for the coming April, and then let your parents understand as well. Right. So that one will be practiced in the part of our syllabus for the next coming subtopic. So remember, please prepare one of your house electric bill so that we can study the bill together. Right. So what is mean by the first 200, 300 unit, next 100 unit, what is that? Okay. So actually this one you already have the basic in the history that you read. So but anyway, come to KBSM and physics, we still continue to study about this one, energy cost and also the efficiency. So after that, then we finish the chapter 2.